Hello, this is Atif, and I welcome you to Base 2's Fast API AsyncIO Foundation course. It's time to understand how AsyncIO works in Python. Looking at the diagram, you can say straight away that it's significantly different from multiprocessing and multithreading. Whereas the former, both approaches are preemptive, AsyncIO is a cooperative multitasking approach. OS does not control the task scheduling in AsyncIO. This gives more control to the Python program over concurrent execution of the tasks. AsyncIO is suitable for IO-bound tasks. Some examples are database reads and writes, file reads and writes, and network operations like posting data to a server or fetching data or content from a CDN. Event loop is the core of AsyncIO. It is a loop running in a single thread, generally the main thread, and it waits constantly for I/O events to occur. As the events occur, event loop adds corresponding tasks or the coroutines to the ready task queue. The coroutines are processed in FIFO order, first in, first out order. The coroutines execute and yield the control back to event loop voluntarily, and this nature makes AsyncIO cooperative multitasking. Normally, the coroutines are lightweight functions, and event loop is able to run thousands of coroutines concurrently. You might ask, what if the functions are not lightweight? This means that we are doing something wrong. This means that they are not IO bound coroutines, rather, they are CPU bound. And in such case, async IO is not the correct choice. One last thing, event loop constantly waits for the events and it adds corresponding coroutines to the ready queue. Which events does it look for? First type of events are IO events, such as maybe a socket is now ready to read or write, a file descriptor has data available, or a subprocess has output ready, or server got a new connection. The second type of events are timer events, such as an API client waiting to retry a failed request in 3 seconds, a background task which is scheduled to run every 10 seconds. And the third type of events are callbacks, such as a file upload finishes and you must notify the user. All right, let's address the main question. Why is FastAPI built upon AsyncIO? FastAPI is a web framework, and it has been built to best suit the nature of web servers. Most obvious of the web server's job is to serve the web pages and web apps. While doing so, they are fully engaged in network I/O. In the meanwhile, they might also be writing data to a database or looking up for the data based on a user's query. Now they are performing database I/O operations. And when a user uploads a file, or when the server has to serve static files from disk storage, it is file I/O. The web servers find themselves dealing with the I/O bound tasks most of the time. Now let's do a comparison of the three multitasking approaches to find the answer to our question. Multiprocessing is suitable for CPU bound tasks. It is a resource heavy approach, so it can be ruled out for the lightweight I/O bound tasks, being an overkill of resources. On the other hand, multithreading with the GIL had been considered an option for IO-bound tasks before async IO was introduced in Python. But it can't be used to achieve the high concurrency and scalability needs of web servers today. Why? Because it requires to span several threads, which gets limited by the number of available CPU cores. This also means that multithreading becomes significantly resource expensive. Lastly, async IO. Async IO's event loop runs in a single thread, which means it is really a resource-friendly approach. With cooperative concurrency, it can run thousands and even tens of thousands of concurrent tasks with the single thread. So AsyncIO is ideal for IO-bound tasks like a web server has to perform most of the time. Due to these advantages, FastAPI has been built on AsyncIO. The existence of FastAPI became possible only after AsyncIO was introduced in Python.